Hey guys, today we're going to be tackling something called implicit differentiation. So we're still going to be using all of our differentiation rules. It's just going to look a little bit different today in that our functions aren't always going to be set up with just some function equals all x values. We're going to sort of mix in some y values as well. So that's going to change things a little bit for us. But we're going to keep in mind all of those derivative rules that we have learned over the past few weeks. So first I want you to consider these two examples here. So if we were to just find the derivative of the first one, it'd be pretty easy. By now we're pretty good at that. This would just be y prime equals 2x. And that would do it. Now the problem is with the second one, it doesn't look like the first one, which the first one is like all of our derivatives that look like, whether it's f of x or r of t or s of a or whatever it is, it's always some function with a single variable on this side, on the right side. However, this one does not look like that. So your first thought might be, well, maybe I could just rewrite it that way, right? Maybe I could just get the y by itself and then we could do it. So we could try that. We could subtract the x squared over. We get y squared equals 4 minus x squared. Now we'd have to take the square root, which, okay, you're thinking, well, I could do the derivative of this. However, the square root of 4 minus x squared is not just positive, it's actually the positive and negative square root of that. So here's where things get a little dicey. Do I want the positive or do I want the negative root? We're going to have maybe a little bit more challenging derivative. It would definitely be doable, but we don't know what to do with this plus or minus part. Now, the reason why is these two functions, the first one we know looks like this, right? It's just parabola that's shifted up 3. The second one isn't actually technically a function, it's a curve, and in fact, it's actually a circle. It's a circle with a radius of 2. So we haven't talked about how do we find the derivative of something that's not a function. In this case, it's a circle. A circle isn't a function because it fails the vertical line test, right? But if we were to ask to find, let's say, the equation of a tangent line at a specific point, maybe at this point, well, we would need to know the derivative of this function. We can't really figure out how to do that with this knowledge that we currently have, so we're going to use something called implicit differentiation, where we can differentiate this from its original form right here. And the way that we're going to do that will look something like this. We're going to start with the original one here. Is we just treat it sort of as two separate two derivatives here. Treat the first one as x squared, it would just become 2x using the power rule. Now with the y squared, we're going to treat it the same way for the most part as we did with the x. We're going to use the power rule as well, so it'll be plus 2y. But we also have to write one additional thing. We're going to write it as y prime. We're going to say that it's 2y, y prime. Because technically what we're doing, we're always applying the chain rule, which we learned in the last one. Even with a function like x squared, we're actually doing 2 times x, and then we're sort of doing the derivative of what's inside of here, if we were to think of it in that way. And the derivative of what's inside there would just be 1. So really, we're actually doing a chain rule with that. It's just the derivative of x is just 1, so this just becomes 2x. And that is because we're differentiating with respect to x. So sometimes you'll see instead of y prime, it would just be dy dx, because we're differentiating with respect to x. So an alternative way of writing this would be 2x plus 2y dy dx. As we get into something called related rates, this will be really important that you know how to do this implicit differentiation, where for now you just need to know that if you take the derivative of a variable with respect to x that's not x, you have to add this, whether it be y prime or dy dx, or if it was even a different variable, let's say if this was a t squared, then this would be 2t, and then you could say t prime, or you might probably more likely see it as 2t dt dx, because you're just saying the derivative of t with respect to x is how you're saying that. So this means the derivative of y with respect to x. In other words, we don't know what the derivative of y is with respect to x, so we're just going to say dy dx. I realize this might be really confusing right now. Just sort of hang with me and get the technique of implicit differentiation down. And then hopefully later and the next chapter, when we actually do related rates, you'll have a little bit better understanding of what this dy dx or dt dx or y prime actually means. So in order to finish this derivative, that 4 would just be 0. And then what we're actually going to do is just solve for the y prime or the dy dx, however we want to classify it. So we're going to get the y prime by itself. So if we were to take this one up here, we would then just move the 2x over. So it would be 2y y prime equals negative 2x. We would then divide by both sides by 2y. So we get y prime is negative 2x over 2y. And that's going to be our answer. That's the answer for our derivative. We ended up able to get y prime. Now notice the answer does have y in the answer. That's not all x's, but that's okay for this. No, but that's how we're going to solve it. The actual definition of implicit differentiation, you could say it's the process of differentiating both sides of an equation with respect to x and solving for y prime. And again, this could be or dy dx. We're just going to write it as y prime for now, but note that in the future we might even want to call that dy dx, or we might even call that like dv dt for volume, or dA dt for area, or anything like that. The definition, again, this is just the book definition. Don't get too caught up on what this means, but it's saying that the derivative, and this actually, sometimes you'll see a dy there, sometimes you'll see a d, but it's saying the derivative of a function of y equals the derivative of that function times y prime. Don't get too caught up in that notation, though, for right now. Let's just do some problems. The important thing with this section for now, like I said, is that you just understand how to implicitly differentiate a function, and the application of that will come later. So let's start with this basic one. It's actually just pretty much the same as what we just did. Take the derivative of x squared, so just 2x, plus the derivative of y squared. You still use your power rule, so it's 2y y prime. Just note that whenever you take the derivative of a y, after that you're going to write y prime. That's basically all there is to it. Equals 0. So that's our first step. Differentiate. First step, differentiate with y prime. And then our second step is just going to be to solve for y prime. So we just get the y prime by itself. We would move the 2x over. So we get 2y y prime equals negative 2x. We then divide both sides by 2y. This cancels. Y prime. These twos can cancel, so we just get negative x over y. And that is the answer we're looking for. Y prime equals negative x over y. So we should always end up with y prime equals something. Let's go and look at the next one. Okay, here. Sorry. Let me just skip some. There we go. All right, with this next one, treat it the same way. So this becomes 2x, the power rule, plus, now y cubed would become 3y squared using the power rule. And then after that, we got to write y prime equals 4. So it's going to work the same way. We're just going to, oh, sorry, that shouldn't be 4. It should be 0. The derivative of any constant is 0. So we just subtract the 2x over just like before. Negative 2x. And then we just divide by everything that's attached to that y prime. It's just all one term. So we just divide by 3y squared to get rid of all of that on both sides. So our answer then is just y prime equals negative 2x over 3y squared. And that's it. Okay. Well, let's look at a little bit more challenging one. Your first instinct on this one might be quotient rule, maybe. Quotient rule, question mark. Whenever you see a fraction, you might think quotient rule. I would not use the quotient rule on this one, simply because it's easier to just rewrite this as xy to the negative third power. It's probably a little bit easier. Just rewrite it. Since the functions are pretty simple, just rewrite it that way. So rewrite, you could, I suppose, do the quotient rule, but it's easier just to rewrite it. When you do that, then you'll actually have to do the product rule. So I guess either way, you'll end up using one of your rules. Typically, you would see it rewritten first, though. All right, so then remember the product rule. You do the derivative of the first thing. So the derivative of x is just 1 times the second. So 1 times y cubed, I'll put them in parentheses now, just to show you the rule, plus, right, derivative of the first times the second, plus the original first, so x, times the derivative of the second. So the derivative of y to the negative third will become negative 3 y to the negative fourth. But since we took the derivative of y, we also got to throw a y prime on there. Equals 1. So our goal remains the same. We're going to try to get the y prime by itself now. I'm just going to go ahead and rewrite this first, though. This is just y cubed. And we'll put that negative out, so it becomes negative 3x y to the negative fourth y prime equals 1. All right, and then we need to get the y prime by itself, so we need to move that y cubed over. Oh, sorry, I did it again. The derivative of 1 is 0. My bad. Oh, I keep doing that. All right, so we'll subtract the y cubed over. So we get negative 3xy to the negative fourth y prime equals negative y to the third. Another thing to be careful of, that y prime isn't y to the first power, it's y prime. It's different than y to the first power because we don't write the 1 up there for the y. Remember, this y prime is equivalent to saying dy dx. We just use y prime. It's kind of a shorthand notation. All right, so then to get the y prime by itself, we divide by everything else attached to it. So we're going to divide by negative 3xy to the negative fourth on both sides. It gets wiped out. So we're left with y prime equals, since we have two negatives, we'll make it positive. And also, since we have a negative 4 on the bottom of the fraction, that would go up and make it positive. So that would actually give us 3, and then we'd actually add the negative, we'd actually add those 4 to the top, so it would become y to the 7th on the top. Because the negative always just tells you to move it to the other part of the fraction. So this actually just comes up as y to the 4th. So then we actually get y to the 3rd, and y to the 4th is y to the 7th. Again, a negative and negative becomes positive, and then we just got the 3x left on the bottom. So that will be our answer. Okay, let's try a couple more here. Notice this one has multiple terms, so it has multiple versions of that y. Let's go ahead and just treat it the same way to start here. So this will become 6y squared using the power rule. And then since we took the derivative of a y, we also got to write a y prime there. Plus 8x minus, now the derivative of y would just be 1. In the same way that derivative of just x would be 1. But since we took the derivative of the y, we also got a y prime there. So I'm just going to say minus 1 y prime. And then we got equals 6x to the 5th. Okay, now this looks a little bit different because we have multiple y primes. But our strategy is going to be to keep all the y primes on the left side, just like before, and then all the other variables to the other side. So that's what I'm going to do first, is just group those. So we want y primes on left, all others on the right. So we end up with 6y squared y prime minus 1y prime. I'm just going to leave the 1 there for now because it will be helpful in the next step, you'll see. Equals 6x to the 5th minus 8x. One thing to note is you can't combine those y primes because they have different terms. The one is a 6y squared y prime. You can't combine that with a 1y prime. Those are not compatible. What you can do, however, is you can factor out using the GCF. So in this case, whenever you have two terms, you're going to factor using GCF. And in most cases, well, I shouldn't even say GCF. I'm just going to just say actually factor out the y prime, which will be the GCF in this case, but just factor out the y prime. Since these both have a y prime, we're going to pull it out, y prime, and then in parentheses, we have a 6y squared minus 1. And you can see why I left that minus 1 with the y prime. It just kind of is a good reminder that we have to put that negative 1 there. Don't just assume it's 0. You still have that 1 left over there. And then we still got our right side, 6x to the 5th minus 8x. So then our last step then, now that we've got the y prime by itself, is then to divide by all of this that is being multiplied by here. So this cancels, and then y prime is this. Not anything you can do to simplify this. Not the most beautiful function, but that is it nonetheless. Right. So again, if you have multiple y primes, group them on the same side together, generally the left side, then you pull out the y prime to create sort of a greatest common factor situation, and then you're going to divide both sides by whatever's in the parentheses there. All right, let's look at a trig function. It's going to work the same way pretty much here. So to implicitly differentiate this one, my first term, 7y squared, that's just going to become 14y, then y prime, because it's the derivative of a y term, plus the derivative of sine of 3x. Derivative of sine is cosine, so it's cosine of 3x. And remember the chain rule, since there's something inside of that, we also have to take the derivative of what's inside of it, which is 3, so times 3. After you get the hang of that, you'll just write it as 3 cosine 3x, but we'll write the whole thing out for now. So that's the first derivative part, equals, the derivative of 12 is just 0, so that just goes away. You could write it as 0 if you want to. Minus 4y cubed, and then y prime. All right, so we want to keep our strategy that we've had, and that is to get all of the y primes on one side and all of the other terms on the other side. I always just like the y primes on the left side, so I'm going to continue that. I'm going to keep this 14y y prime here. I'm going to move my other y prime over, so I'm going to add over that plus 4y cubed y prime equals, and then I'm going to subtract over that cosine of 3x times 3. So that's going to become a negative 3 cosine 3x onto the other side. So I've just reordered stuff, switched them sides using the inverse operations. Okay, once I get to this point, I'm just going to pull out my y prime. So then I'm left with 14y for my first term plus 4y cubed for my second term equals negative 3 cosine of 3x. And then I'm going to divide both sides by what's in that parentheses. 14y plus 4y cubed. Make sure you're writing out these steps too. Don't get lazy and skip these steps. It's not going to kill you to write a little extra. So my final answer then is y prime equals negative 3 cosine of 3x over 14y plus 4y cubed. So hopefully you're starting to get a hang of the strategy here. It's really not really any more difficult than what we've done before. It's just the added step of adding on the y prime whenever you differentiate the y, and then you got to solve for it, get it by itself. But generally, the derivative parts are actually easier. Now let's go and try another one here. So this first term here, notice it's the product of two things, so this is actually going to be a product rule. So we take the derivative of our first term, which is the 4x squared, so that's going to be 8x y to the 7th, keep our second term, plus keep our original first term, 4x squared, times the derivative of the second, which would be 7y to the 6th, And then always got to throw on that y prime whenever we take the derivative of the y. So we took the derivative of the y on the second part of the product rule, we throw on the y prime. Okay, then it's going to be minus derivative of 2x is just 2 equals 5x to the fourth plus 12y squared. Since we took the derivative of y, we got to throw on a y prime. Sorry, this thing's weird. All right, throw on the y prime. Okay, let's just simplify this a bit and group all of our y primes together. I just always identify those terms. Here we got a y prime in this one and a y prime here. So I'm going to bring those to the left side. This term, just to simplify that a bit, that will become 28. 4 times 7 is 28. X squared y to the 6 y prime. And I'm going to be moving that 12 term over. So it'll be minus 12 y squared y prime equals, we've got that 5x to the fourth on the right side. I need to move over the 8xy to the seventh. So I'm going to do minus 8xy to the seventh. And then I'm going to add the 2 over. So I've only got y prime terms on the left side. Now I'm going to factor out the y prime. So we're left with 28x squared y to the sixth minus 12y squared equals 5x to the fourth minus 8xy to the seventh plus 2. And then I know I'm going to divide on both sides by this 28x squared y to the sixth minus 12y squared on both sides. Does not look prettiest again, but this is your final answer for y prime. Just going to write it out. Y prime equals 5x to the fourth minus 8xy to the seventh plus 2 over 28x squared y to the sixth minus 12y squared. There we go. Again, the derivative part of this actually isn't so bad. You'll find these easier than probably the last section of the chain rule. Just adding an extra step there. All right, and let's try one more little challenging one here. Yeah, before we get to our equations. I think this one should be sufficient. All right, so this one does have a chain rule involved in it. When we take this derivative, first of all, if cosine is minus sine, so remember it's like the minus sine of u times u prime. So we're going to keep the inside the same to start. So minus sine of x squared plus 2y times y prime, or sorry, u prime. So it's going to be times 2x plus 2y. Oh, sorry. I am off my game there. So 2x, and now this term, when I take the derivative of that, 2y is just going to be 2y prime. All right, because again, the derivative of 2y would just be 2, because y to the first power, but then anytime we take the derivative of y, we got to throw on the y prime. Hopefully, didn't confuse you too much on that. We took the derivative of the outside minus sine, kept the inside, so it's like the minus sine of u times u prime. The derivative of x squared is 2x. The derivative of 2y is 2y prime. And we've got some more to do. Plus, we have a product rule here. So derivative of x is 1 times e to the y squared plus derivative, the original first, which would be x. And then the derivative of e to the y squared would be e to the y squared, because e to the u times u prime. So that derivative would be 2y. Since I took the derivative of y, I got to throw in a y prime. Equals 0. All right, this is kind of a mess here, but we'll get it sorted out. With this first term here, what we're actually going to want to do is go ahead and distribute. So I'm going to go ahead and multiply this times that. So we're going to distribute this whole big first term times both of these. Again, it won't look pretty, but let's do it. We'll get negative 2x sine of x squared plus 2y. Notice that is not a y prime term. And then minus 2y prime and actually should only throw the y prime on the end. So it's going to be minus 2 sine x squared plus 2y y prime. So when I distribute that one, plus our e to the y squared. And then here, I'll just reorganize that one a little bit, make it 2xy e to the y squared y prime equals 0. So I just reorganize that last term a little bit. Then I want to get all my y primes on the left side. So I'm going to keep this term and this term on the left side. So I have minus 2 sine x squared plus 2y, is y prime, plus 2x y e to the y squared y prime equals, need to move this one to the right and this one to the right. So that will become my plus a positive 2x sine of x squared plus 2y minus e to the y squared. I then need to pull out my y prime. So y prime equals negative 2 sine of x squared plus 2y for my first term, plus 2x y e to the y squared equals the right side stays the same. And last but not least, I want to divide both sides, and I'm just going to do this in one step here. So I don't think you want to watch me rewrite all this twice. So my final answer is going to be that divided by negative 2 sine of x squared plus 2y plus 2xy e to the y squared equals y prime. And that is about as complicated as it will get for you. I think we're going to end there. We will save the tangent line problems for another day. If you are struggling with this or just struggling keeping up with the derivative rules in general, please reach out to me. I can organize a time to meet with you, help you through them. I know you're getting a lot of rules and it's probably getting confusing at this point. Believe it or not, we're actually going at a pretty slow pace. Ideally, I'd like to be a lot further ahead, but just the nature of this year is unfortunate, and we're going to just persevere and do the best that we can. So again, if you do need help, please don't hesitate to reach out to me. All right, thanks, guys.